The cosmos, in all its vastness, presents us with an array of challenges and opportunities. One of the most pressing challenges we face on Earth is the quest for sustainable energy sources. As our reliance on fossil fuels continues to impact our planet, the need for cleaner, more sustainable alternatives becomes increasingly critical. Among the many promising avenues being explored, the conversion of carbon dioxide into valuable chemicals and fuels stands out as a beacon of hope. Imagine a future where we can capture the carbon dioxide emissions from industrial processes and transform them into methanol, a versatile fuel and chemical building block. This is the tantalizing promise of carbon dioxide hydrogenation, a chemical reaction that converts carbon dioxide and hydrogen gas into methanol. While the concept is simple, the execution is anything but. To unlock the full potential of carbon dioxide hydrogenation, we need catalysts, materials that can accelerate the reaction without being consumed. And at the forefront of this catalytic revolution are cobalt-based catalysts. Cobalt, a metallic element with a silvery blue hue, might not be the first thing that comes to mind when you think of catalysts. Yet, at the nanoscale, cobalt nanoparticles exhibit remarkable properties that make them ideal candidates for carbon dioxide hydrogenation. These tiny particles, typically dispersed on a support material like silica, act as miniature reaction centers, providing a surface for carbon dioxide and hydrogen molecules to interact and react. The choice of support material is crucial, as it can influence the size, shape, and ultimately the catalytic activity of the cobalt nanoparticles. Silica, a common and inexpensive material derived from sand, provides a stable and porous framework for the cobalt nanoparticles. Its large surface area allows for a high dispersion of cobalt, maximizing the number of active sites available for the reaction. However, even with silica as a support, the performance of cobalt catalysts can be further enhanced. This is where the ingenuity of materials science comes into play as researchers explore the addition of other elements known as promoters or additives to fine-tune the catalyst's properties. Think of cobalt nanoparticles on silica as the foundation of a house. The foundation provides the basic structure, but it's the walls, windows, and roof that make it a comfortable and functional home. Similarly, while cobalt nanoparticles provide the basic catalytic activity, metal additives act as the walls, windows, and roof, enhancing their performance. These additives, often metals like magnesium, calcium, titanium, aluminum, or zirconium, can be introduced during the catalyst synthesis process. They interact with both the cobalt nanoparticles and the silica support, modifying the catalyst's structure and electronic properties. Magnesium, for example, can promote the formation of smaller cobalt nanoparticles, increasing their surface area and thus their catalytic activity. Calcium, on the other hand, can enhance the stability of the catalyst, preventing the cobalt nanoparticles from sintering or clumping together during the reaction. Each additive brings its own unique set of properties to the table, and researchers are constantly exploring new combinations to optimize catalyst performance. It's like a chef experimenting with different spices to create the perfect dish, carefully adjusting the ingredients to achieve the desired flavor profile. Now, let's zoom in to the nanoscale, where the real magic of carbon dioxide hydrogenation happens. Imagine a cobalt nanoparticle on a silica support, surrounded by a sea of carbon dioxide and hydrogen molecules. The first step in the reaction is the adsorption of carbon dioxide and hydrogen onto the catalyst surface. This is where the choice of additives plays a crucial role, as they can influence the binding strength of carbon dioxide and hydrogen to the catalyst. Once adsorbed, the carbon dioxide molecule undergoes a series of transformations. The strong cobalt-carbon bond weakens the carbon-oxygen double bonds, making it easier for hydrogen to attack the carbon atom. This leads to the formation of various intermediates, molecules that exist for a short period before transforming into the final product, methanol. These intermediates are like stepping stones, guiding the reaction along a specific pathway. Section 5. Key intermediates, formate and methoxy. Among the many intermediates formed during CO2 hydrogenation, formate or HCuO and methoxy or CH3O stand out as key players. These two molecules represent branching points in the reaction pathway, influencing the selectivity of the catalyst towards methanol. Formate, formed by the insertion of hydrogen into the carbon-oxygen double bond of CO2, is a relatively stable intermediate. It can either decompose back into CO2 and H2 or further react to form methanol. Methoxy, on the other hand, is formed by the addition of hydrogen to the carbon atom of formate. This intermediate is considered a precursor to methanol, as it can readily react with another hydrogen atom to form the desired product. The relative abundance of formate and methoxy on the catalyst surface is a delicate balancing act, influenced by factors like temperature, pressure, and the choice of additives. Understanding the interplay between these intermediates is crucial for designing catalysts that selectively produce methanol. Section 6. Unlocking the secrets, cobalt reducibility. To truly master the art of catalyst design, we need to delve deeper into the properties that govern their performance. These properties, often referred to as materials genes, are like the DNA of a catalyst, dictating its behavior and ultimately its effectiveness. One such gene is cobalt reducibility, a measure of how easily cobalt oxide, or CuO, which can form on the catalyst surface, can be converted back to metallic cobalt, or company metallic cobalt is the active site for CO2 hydrogenation, so a highly reducible catalyst is desirable. Visualize cobalt oxide as a rusty nail, its surface covered in a reddish-brown layer. Upon reduction, the rust disappears, revealing the shiny, metallic cobalt underneath. The easier it is to remove the rust, the more active the catalyst will be. Additives can significantly impact cobalt reducibility. Some additives, like zirconium, can donate electrons to cobalt, making it easier to reduce cobalt oxide. Others, like aluminum, can form mixed oxides with cobalt, altering its electronic properties and enhancing its reducibility. Section 7. Adsorption strength, the key to efficient binding. Adsorption strength describes how strongly molecules like carbon dioxide and hydrogen bind to the catalyst surface. The Goldilocks principle applies here. The binding strength should be just right. If carbon dioxide binds too weakly, it might not adsorb onto the catalyst surface. If it binds too strongly, it might occupy active sites, preventing other molecules from reacting. The same principle applies to hydrogen adsorption. Section 8. The chemical symphony, additives and their influence. The choice of metal additives is akin to composing a symphony, where each element plays a specific role. Each additive brings its own unique chemical personality. Electron affinity dictates how readily an additive will donate or accept electrons. Additives with high electron affinity, like vanadium, withdraw electrons from cobalt, while those with low electron affinity, like zinc, donate electrons. This interplay influences the catalyst's electronic structure and performance. Section 9. AI takes the stage optimizing catalyst with machine learning. Designing the perfect catalyst is a complex puzzle with countless combinations to explore. This is where artificial intelligence steps in, accelerating the discovery process. Machine learning algorithms analyze vast data sets, identifying patterns and relationships. They predict new catalyst performance, guiding experiments towards promising candidates. Section 10. Conclusion. A sustainable future fueled by innovation. As we stand at the precipice of a new era in materials science, the convergence of nanotechnology, catalysis and artificial intelligence holds immense promise for addressing global challenges like climate change. Carbon dioxide hydrogenation, powered by cobalt-based catalysts and guided by AI, offers a glimmer of hope for a more sustainable future. The ability to transform carbon dioxide, a greenhouse gas, into methanol, a valuable fuel and chemical building block, is a testament to human ingenuity. And as we continue to unlock the secrets of catalyst design, we open doors to a future where we can harness the power of chemistry to create a cleaner, more sustainable world. From the nanoscale reactions on the catalyst surface to the macroscopic impact on our planet, the journey of carbon dioxide hydrogenation is a testament to the interconnectedness of science, technology, and the cosmos itself.